The South Pole isn't an obvious place to build a telescope. Winter temperatures go down to about minus 100 Fahrenheit. Add the wind chill and you get about minus 155. The reason we've come here is because it's such a good spot to look at the cosmic microwave background. The cosmic microwave background is often referred to as the leftover light from the Big Bang. It's the earliest light that we can see. Light that was given off only a couple 100,000 years after the Big Bang. It's got little hot spots, little cold spots, bumps and wiggles scattered throughout it. And by looking at exactly how those are distributed, we can see sort of a picture of exactly what the universe looked like way, way back then.
Ready?
Let's go. Luckily, it's a flat road.
That's what the South Pole does, right?
It tests you.
We installed the South Pole telescope in 2007 because it's the best observing site in the world for doing this kind of observing. And the reason is that it's so cold and we're effectively on a mountaintop.
Okay, be careful of that, all right? Don't let it slam down on you.
So we're at an altitude of about 10,000 feet, and the atmosphere is so cold that the water vapor is frozen out of it.
Right now it's about 30 below, but the wind's not too bad, so the wind chill's probably 40 below.
We also like to observe when the sun is down. And the sun is down for 6 months of the year. That's when we do relentless observing. In the summer months, we can do maintenance on the system, do repairs, put in a new camera, things like that.
Right now we've got the telescope coming in from its nominal observing position to its dock position, so basically coming into park. And it kind of zooms down real fast until it gets to about 3 feet away and slows down and comes in nice and soft. But it's pretty exciting when you got it coming in fast like that. It's a pretty big machine just swinging down at you.
The primary goal of my trip is to replace some of the optics in the existing telescope with their counterparts that are appropriate for the new camera that we'll be putting in.
The new camera being installed this summer is a polarization-sensitive camera. That is, instead of just seeing the brightness of the microwave background, it can see the polarization. Fundamentally, light is an electromagnetic wave. It's just an electric field that goes up and down and up and down and up and down, and a magnetic field doing the opposite. And if the electric field goes up and down, it's one polarization. If it goes side to side, it's another polarization. There are two main things that we're looking for with the new camera. The first is called inflation. Our current understanding of cosmology holds that about 13.7 billion years ago we had a Big Bang. And immediately the universe expanded incredibly rapidly. That period is called inflation, and it's something that physicists have been trying to wrap their minds around for about 30 years since it was first proposed. In order to see inflation, you need some very specific marker. And one of the markers which has been proposed is a polarized signal, which would be visible in the cosmic microwave background.
This polarization signal is a thing which we haven't seen yet, but we think might be there. It's the effect of gravitational waves that, in theory, would be created during inflation. And these gravity waves would just kind of stretch space And as they stretch the space, they actually impart some polarization on the light that's emitted to us. And that allows us, going backwards, if we look at that polarization and we see the correct signature, we can actually say, there were gravitational waves there, which would be another piece of evidence in our hands that this crazy thing, cosmic inflation, actually happened.
So this is roughly what the telescope does. It goes back and forth at constant elevation and steps up a tiny bit. It goes back and forth. The other thing that we're trying to do is to use the cosmic microwave background as a backlight, because after those photons were released 14 billion years ago, they've been coming towards us the whole time. And along the way, they go through and interact with all sorts of things. Specifically, if they pass through a big cluster of 1,000 galaxies, they can get knocked around in energy a little bit. And you end up with a little shadow sort of cast on the microwave background. So by looking for these shadows, we can identify where there are giant clumps of matter in the universe. And we can build up this census of what was in the universe at every slice in time. So if we take all of the big clumps of matter that we discover that are 1 billion light years away, and then all the clumps of matter 2 billion light years away, all the clumps of matter 3 billion light years away, you can say what the universe looked like 1 billion years ago, 2 billion years ago, and 3 billion years ago. So if we look at that field another way, move this over to here, and I'm just going to change the color to grayscale so that you can see the clusters a little bit more easily. And here you can see some very, very obvious galaxy clusters, these big black dots.
So the difference between this map and the other one is just that this one is heavily...
We're looking at light 14 billion years old hitting our camera. It's kind of cool to just think about almost the time travel aspect of it. Like we're looking so far into the past to a time that is almost incomprehensible compared to the way the universe works now.
One of the great things about experimental physics is that you don't just get to learn physics. I've spent a lot of time greasing the telescope. I've spent a lot of time working with vacuum systems and wandered around outside in the middle of winter in the Antarctic. It really takes you across the field of engineering and physics and math. It really gives you an incredibly broad